So Dr. Vasilii Shelkov is a physicist, entrepreneur, and the co-founder and CEO of Rockflow Dynamics, RFD, the company behind the high-performance reservoir simulation navigator. He earned his PhD in high-energy physics from the Southern Methodist University and conducted postdoctoral research at Lawrence Berkeley and Brookhaven National Laboratories. With experience spanning both academia and industry, including roles at UCOS EP. He co-founded RFD in 2005 to develop advanced numerical solutions for reservoir simulation. Under his leadership, RFD has grown into a global technological company with around 500 professionals, marking 20 years of innovation in 2025, as of 2025. He's based in Houston. Dr. Shelkov continues to drive advancements in integrated subsurface simulation technologies. In addition to chairing today's seminar, Dr. Shelkov will speak on fully coupled geomechanics and present a live demonstration of a fully coupled geomechanical simulation using SPE10 model. Dr. Shelkov, please, you can take over.
All right, thank you, Coffee, so much.
Okay.
And thank you, PetroSkill Virtual Learning for inviting me.
Okay.
So let me share my screen. So what's going to happen, I'm sure I'm going to show you some introduction to actually sort of advanced topic. So we start from the end, we assume everyone knows everything. And so everyone is an expert, which is great, right? And then we basically discuss some advanced features based on live demo. So live demo is always better than PowerPoint because you see moving pictures, you see things that I make, mistakes that I make, you see the actually live software, which is much more fun. And to start, I'll just do a small introduction just to describe what exactly I'm going to talk about. And then I show the real calculations, real demo. And then we'll be sort of open for the questions if you have any questions. Okay, so let me share the screen. Okay, so okay. Do you see it?
You can see it. You can see it.
Yes, it's okay.
It's okay? Okay.
Yes.
All right, so let me. Is it fine? Yeah, okay. So so the name of the presentation is Fully Coupled Geomechanics, the best kept secret of T-Navigator. And so last year we celebrated 20 years of T-Navigator. It's hard to believe. I feel like we started yesterday. I guess you will see the same about PetroSkill startup. Sooner or later, you will realize it's been more than 1 month. It could be 10 years, 20 years. So it's a good thing. The simulator, the part in T-Navigator, we have different things. So in principle, you can stay within the framework of T-Navigator, make different and kind of fulfill different pieces of the workflow of reservoir engineer, of geologist, geoscientist. Some of these pieces more advanced, some of these pieces in sort of middle of development, but overall it's a fairly powerful tool that allows you to study physics, to make predictions, to analyze the economics, and do pretty much everything that you are supposed to do working for oil, by exploration, production, oil company or gas company or service company. So the topic. So most of the simulators, most of the engines, right, that allow you to run composition, black oil, thermal models, different physics, they concentrate on something that takes place inside the pore volume, right? So you have like looking at this picture that I took from there's a reference from LinkedIn. So there is a volume where you have fluids, where you have gas, and this fluid sort of filtrate, right? So that's why we would like to use calculators. We use simulators to predict where the fluid or gas will sort of flow and migrate, filtrate. And but there is another sort of hidden physics behind it or around it. You know, there is a stress. There are rocks, right? The rocks don't, in most cases, don't move too much, right? But they talk to each other. They actually hold the structure together, and this structure can be described by stress distribution. This is how these rocks talk to each other. And you know, in many cases, you don't need the stress distribution, or you don't need to know about what's going on inside the rock structure, as long as you don't change the pore volume, as long as you break the rock. You know, and pretty much that's what most of the simulation reservoir simulation is doing. You know, they just calculate the things that happen in the pore volume, right? Don't nobody, you know, people, because like everything, once you bring more physics, it becomes more complex, it takes more time, and so on and so forth. So it's very difficult to include. In many cases, you don't need to, right? But as we go to CCS, the carbon storage, carbon you know, like EOR, where you do fracking, where you inject too much. You know, there are you as you go to more and more complex fields, away from sandboxes, away from bread and butter, kind of easy to get oil, you start to worry about geomechanics. And because sometimes rocks break, sometimes you actually get the things near the, for example, fault, where you can, for example, drop pressure too much or inject too much, and you can change the properties of the faults. So you know, you start to worry that you know, maybe I have to actually model what's going on inside the rock walls, not just the pore volume. So this is like a system of equations. So basically, the the first two equations and the fourth one is the what you need to know about the flow, right? Flow of liquids and gases, and dissolved gases and liquids. And geomechanics is equation number three. It's in this case it's elastic. Elastic means it actually behaves like a spring. So you press it, it can go up and down. And then you can add non-elasticity. You can add the failure criteria. You can actually try to change the properties as you go through the time steps, and you know, depending on some kind of failures. And the good thing, like in industry, you usually solve these systems in separate pieces of software. So you buy one very expensive piece which allows you to do you know, like filtration, or you know, like the reservoir simulation, and you buy even more expensive piece of software that allows you to calculate the geomechanical part. So equation number three plus extra terms for non-elasticity, other things. And you then try to make this software talk to each other, and it's very outdated and you know, kind of not so easy to do, and super expensive way to study your physics and study your production forecast, for example, right? So what we did in TNAV, we actually put this engine behind the scenes. So you know, like you can take any model, you can change few keywords. I'll come to this in next slide, and you can turn on the fully coupled geomechanics. Fully coupled means that simulation and rock stress calculation, all these equations plus some others, they actually calculated and they numerically resolved in one big system. Technically, it's very complex because you have to change grids. So for simulation, you use finite volume, finite difference for time. approximations, and for geomechanics you need a finite element approximation. So you see on the right that you have to actually create tetrahedral grids. So we do it automatically for you, so you don't have to worry about this. You have to worry about the boundary conditions. You have to include the thermal effects if you'd like. There are many details, but the main idea is that, you know, TNAV allows you to do simulation and rock physics in one, rock stress physics, geomechanics, to be in one place and solve it at the same time. So there are two approaches. So why we call it the best kept secret of T-Navigator, because when you look at the interface, there is no button, there is no icon that says geomechanics. So if you go through network designer for surfaces like HM, fracture designer, you know, the seismic mining, PVT designer, there is no name geomechanics, but it's there. You know, you don't see it, but it's there. And so it allows you to do basically take two approaches. One approach is very detailed. This is what I'm going to show you, like an example of the model which already been built. And the second approach is a quick screening. So you take any model you have, can be any physics, can be composition, thermal, black oil, and you just add 3 keywords. Basically, I mean 3 types of keywords. You flag the TNAV that you want geomechanics. You specify Young module Poisson ratio, and if you want to add some the thermal properties, you add, and you push the run button, right? So what we did, we took famous, this is work done by our colleague from Canada, Calgary University of Calgary, Hamid Reza Hamdi. He took SPE10 and extended all the way to the surface. You know, SPE10 is a small piece of the bottom of the North Sea, right, in Europe. And so he built up the overburden, all the layers that don't participate in the filtration or production of oil or gas, but they provide the stress. And so, you know, in a detailed approach, you have to specify all the properties. So you can see the layer by layer, different properties. On the right, you can see the references where these numbers are coming from. You specify basic property for elastic and non-elastic things. Then you specify boundary conditions, that you specify some sort of dummy properties, filtration properties for the overburden, underburden, just to get it working. And then, so what's inside, we in addition to elastic, we had the properties, so sort of ring, spring sort of behavior. We simulate shear and tensile failures, but in this period of time, none of them happened. So basically, we didn't destroy the rock. And also we use one Mises, very simple, that doesn't require too many external data to be provided, an elastic, non-elastic model. So it's not very simple model overall. And so let me just go ahead and show how it looks like live, right? So, okay, so this is T-Navigator. So what I'm going to do, I'm going to point, right, to the model that I can actually show you what that model looks like, how it looks like. So you can see some settings, and this is key thing. It's GeoMech. We basically say we would like to extend this model, which is in one of the industry formats. You can see familiar keywords. And I specify I'd like to turn on geomechanics, right? And this sends a signal to T-Navigator to do many things. First of all, you have to change the grid. We actually generate additional grid, which is like shadow grid of tetrahedrals based on the grid that's supplied with the model, with your simulation model. Then we change the interface to accommodate new, new maps, right? Because you have many more parameters. You're going to see it in a sec. And then you supply this includes. So, but it's basically the same model you've been running, except you have to add few other parameters and the signal that you're gonna go through GeoMechanics. That's all. So it's very easy to do. All right, so we open this model. So this is what the T-Navigator is doing. It loads the model, it gets the keywords, it starts to generate on the fly. I'm running this on the laptop with 32 gigs. So the memory is rather extended for a normal laptop, 32 gigs, but it's a normal laptop. So it has a graphical card that we are going to use. So T-Navigator, once you run fully coupled with the simulation, GeoMechanics, we usually offload this linear part. So linear solver is resolved on a GPU, but everything else is done on the CPU. Okay, so this is model already loaded. What you can see, there is a button. So there is a layer. So basically the SPE10 is a little layer you will see soon. On the bottom here, and then there are all these layers which take you to the bottom of the North Sea. So, and here on the top, you basically assume the boundary condition, pressure from the water, right, and the air above, right. So this is we can remove it. So this is normal grid that we use for simulation. This is tetrahedral grid that is generated automatically. You see this all this additional structure. So as a drop, I mean, sort of the overhead is obvious, right? You have to keep the second grid. And so you, instead of 1 million active grid blocks, which is for the full the model, you end up with 1.6. So it's like 1.6 times bigger grid. You need more memory to run it. But and then you immediately see the additional parameters. So instead of just pressure, so we go to the interface of T-Navigator. Instead of, in addition to pressure, saturation of oil, you get all these tensors, different parameters of the normal stress, of the shear stress, components, deformations, and so on and so forth. So this automatically added. Okay, so how do I, what do I do to run it? I just press the button the same way as you're doing with any sort of reservoir model that you use the T-Navigator for, right? So we go, let me just run one time step, and I'll show you how the resources are used. So you see the CPU is busy. GPU busy, but not much because it's just a linear solver. But still, we take 2 gigabytes of GPU. So it's running. Let's wait for the first time step, and let me. It's probably take a minute or two. Yeah. Okay. So let me stop. So we calculated 12 hours. So we calculated 12 hours of simulation. So let me go and just to provide you better vision, better view, let me just remove some grid blocks. So, and keep just two, number 18. It's the one on the top. That's a piece of the overburden, and then one on the bottom. So what you can see here, let me zoom in, is the following. So we calculated first time step. So yeah, so okay. You see this is SPE10 1 million model that not every simulator can calculate. Some simulators takes a very long time to do it. We do it like if you have a GPU laptop, it takes like less than 2 minutes to run the entire model. So this model is basically squeezed by the top layers overburden and the bottom layers and side burdens. So streamlines inside, so you see this little like a cake inside. The different colors mean different wells. So each color is assigned to a specific well, and this you can actually see how this is distributed. So the first thing, the first thing you can see is the displacement in Z. So we only pumping water. So this injector and for producers, we pumping water for 12 hours, and you see on the top there is a green distribution, blue distribution. It's blue because it's negative. Z points down. It means, and on the bottom it's a different color. It's red, right? So it's positive. So as C points down, basically what we see, the first effect of the beginning of injection, that you sort of inflate the balloon inside your reservoir. So you're pushing layers up and you're pushing layers down. And when you drop the pressure to produce the oil, you see that the opposite things happen around the production wells. So this is the first effect that you immediately see in your model. And you know, if you just run a reservoir simulation without fully coupled approach, you will never see this distribution. You know, you actually are totally unaware what's going on. Now you see. And so what we can look at different things. We can do, for example, look at effective stress. We can look at, for example, full displacement vectors, max stress, and so on and so forth. So what I'm going to show, I mean, just one more thing. We can use T-Navigator, a cool interface, and introduce the filter. So in filter, we basically say, show me only the areas where the displacement in Z, and we are talking about the you know, millimeters of what, I mean, some pieces of millimeter, fractions of millimeter. Actually, use this. Only show me the regions where the displacement is large, and keep updating. So TNAV is super interactive, so you do everything in real time, and you cannot do it with other simulators. So we bring all the layers, and we specify, remove the underburden, overburden, show me the areas where the displacement is the largest, right? And after this, you can look, for example, of total displacement vector. So you see how this things can remove streamlines distributed. So you see where the most of the action is going on in 3D. All right, and then you can look at the maximum stress. You see the lots of stress on the bottom near the injector, and then you can look at the different parameters of the stress tensor as well, shear stress, normal stress, and so on and so forth. And you just can press the button and say keep on going. So I mean, we didn't have to restart anything, we didn't have to export files, we can do everything interactively. So this is why we call it best kept secret. And I guess now it's a good time for to actually learn how you build together, how you put together a good reservoir model, and how you can do it, and what's available. But this is sort of ultimate analysis tool for you to combine simulation and geomechanics. I guess that's it. Sorry, I took a little bit more time than I planned.
Don't worry.
Questions,
Don't worry.
comments? Okay.
So please